Welcome to the Chidon's Academy UNN, where we offer proficient learning solutions that will help you to understand appropriately and be able to go ahead and work with the knowledge that you have gained. I am David Ede, and today we are going to be looking at stereochemistry, which is going to cover the aspect of optical activity and its relationship with drugs. The first aspect we're going to be looking at is optical activity and chirality. But before we go further, we have to understand exactly why we have to be talking about optical activity as it relates to drugs. Now, the issue of optical activity is going to be taught appropriately. So just follow me carefully while we make progress in this particular lecture. So the first thing I'm going to be highlighting is the incidents that occurred some years ago, which happens to be that of thalidomide. Now, when thalidomide was initially introduced, it was introduced as a wonder drug because of its sedative effect. Now, that sedative effect is usually used on pregnant women to treat morning sickness. But then it was realized over time that children that were given birth to by those women had some defects, and that we refer to as teratogenic effect. So those teratogenic effects happens to be teratogenic simply means that the embryonic development of the child was interfered or interrupted. So there are other agents that actually can cause teratogenic effect, like alcohol, like X-ray, but thalidomide happens to be one of them. Thalidomide happens to have two mirror images that are non-superimposable on each other. What do I mean by non-superimposable on each other? If you look at a structure like this, this is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen, and then you put something that looks like a mirror here to mirror this particular image. You're going to be seeing this also on this side. So this hydrogen is this hydrogen, this hydrogen is this hydrogen, this hydrogen is this hydrogen, and this hydrogen is this hydrogen. If you take this compound and put on this compound, they are both superimposable because they are having the same things around the different four bonds. But then that is not the case for thalidomide. Thalidomide mirror images do not superimpose on themselves. You understand better as we make progress. So it was later realized that the S enantiomer, which I'm going to be explaining, was actually responsible for the teratogenic effect of thalidomide, while the arrow enantiomer is what is responsible for the sedative effect that is necessary for the treatment of morning sickness in pregnant women. So before we make progress, we are going to be looking at isomerism. Now, from isomerism, we can now make progress to the aspect that concerns us, which is stereochemistry, stereoisomerism, and then moving down to the optical aspects of it. So let's make progress. What are isomers? Isomers happens to be compounds that have the same molecular formula, but then they have different arrangements. Those are isomers. Isomers refers to compounds that have same molecular formula, but they have different arrangements. Now, isomers happens to be divided or categorized into different groups. So isomers are divided into different categories. Like I already mentioned, isomers refers to compounds that have same molecular formula, but they have different arrangements. So basically, isomers are divided into two categories. We have the constitutional isomers. Constitutional isomers, also referred to as structural isomers, and then we have the stereoisomers. So we have the stereoisomers. Now, what do we refer to as constitutional structural isomers? As you've already seen from the name structure, these particular compounds, they have same molecular formula, but their difference is captured in their structure. Now, constitutional isomers or structural isomers happen to be of three different types. Now, we have the chain, we have the positional, and then we have the functional. So our focus today is actually on the stereoisomers, but for the sake of understanding, I'm going to explain this clearly before we move over to the stereoisomers. So what do we refer to as chain isomerisms under constitutional, also known as structural isomers? Now, in chain isomerism, what we are concerned about is the fact that the difference between the two compounds happen to be that in the structure of their carbon chain. Carbon chain refers to the connections of the carbons in the organic compound. And for you to understand appropriately, I'm going to be giving a very good example. For example, a compound that has the molecular formula C4H10. C4H10 happens to be a molecular formula for a compound, but then we are going to draw out two compounds that have this same molecular formula, and then you see what I meant by chain isomerism being a function of the difference in the structure of the carbon chain. So when we have carbon linked to carbon, linked to carbon, linked to carbon, we are having 4 carbons there, which is corresponding to this. Then we have hydrogens that are attached to these particular bonds. So this is hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this happens to be butane, which is the 4th member of the alkane family. It has this molecular formula, but then I want to draw another structure that has this same molecular formula. Now here is the second structure. We have carbon linked to carbon, linked to carbon, and then we have another carbon here. Now I'm going to be attaching the hydrogen. This is hydrogen, this is hydrogen, this is hydrogen, hydrogen, hydrogen with a bond, and then hydrogen with a bond, hydrogen with a bond here. Then we have hydrogen, we have hydrogen, and we have hydrogen. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 hydrogen, and how many carbons do we have? We have 1, 2, 3, 4. So it also has the same molecular formula, but what's the difference? The structure of the carbon chain. Here we have a straight chain carbon of butane, and then we are having here a branch chain carbon arrangement. And this particular compound, for us to name it, you have to look at the longest chain here. You can either decide to go this way or go down this way, but it's 3 carbon, that's what makes up the longest chain. So this happens to be a propane, but then we have a methyl group attached to carbon number 2, because we can decide to number from here 1, 2, 3, or we can number from here 1, 2, 3, or choose anywhere we want to go, but you also realize that this is the carbon number 2. So this particular compound is 2-methyl propane. Meanwhile, this particular compound happens to be butane, or you can call that your N-butane. So butane and 2-methyl propane happens to be chain isomers. I hope you are getting me very clearly. So the next one I'm going to be talking about is the positional isomerism. Alright, so positional isomerism happens to deal with functional groups that are in a compound, but then they are in different positions. So when you have compounds that have same molecular formula, but the arrangement of their functional groups is just different in different positions, then what we have there refers to positional isomerism. I'm going to be giving a very good example in this particular lecture guide. So let's look at this now. We have 1, 2, 3 carbon atom, and then we have hydrogen, we have hydrogen, we have chlorine here, we have hydrogen, we have hydrogen, we have hydrogen, we have hydrogen, and then we have hydrogen. So this compound happens to be 1, 2, 3, that's 3 carbon. Then the hydrogen is 1, 2, 3, 4, 5, 6, 7 hydrogen, and then we have 1 chlorine atom. Now what we call this, based on the position of the Cl, we refer to this because it's on the carbon number 1, this is carbon number 2, this is number 3. We have to start from here because of the presence of the chlorine atom. So this happens to be 1 chloropropane. This is 1 chloropropane. Now let me draw the positional isomerism for this particular compound so I can illustrate it. Now we can also have a compound that is this way and also having 7 hydrogens, but then the difference between the two of them happens to be the presence of the chloride atom on the carbon number 2. So we have 1, 2, 3. So this particular arrangement is going to refer to as 2 chloro 2-chloropropane. Now, two of them have the same molecular formula C3, H7, and Cl, but the positions of the functional group is different. Here we have it on carbon number 1, while here we have it on carbon number 2. So that is that about positional isomerism. So the next one we'll look at under constitutional structural isomers refers to functional isomers. Now, functional isomers happen to be isomers that occur with different functional groups but same molecular formula. You're going to be seeing what I'm talking about the moment I work on this particular structure. Now we have this. We have this, and this compound has 2 carbon, C2, it has 5 hydrogen, H5, and then it has an OH group. This happens to be an ethanol. This is ethanol. I don't know if you're getting me. This is ethanol. This is 1, 2. That refers to the 8. Then we have the OH group, which refers to the alcohol or the alcoholic group. So this compound is ethanol. But then we can also have another compound that has this particular molecular formula but a different functional group, and let's look at that particular compound. So we have C. Okay, we have C. Let's do it this way. All right, so let's look at this very carefully. Now this is okay. I can actually, this compound, because we have hydrogen and high hydrogen here, we can also write this as C2H6O as the appropriate molecular formula. So we can also count this and see how many carbons and how many hydrogen we have here. We have 1, 2, that's 2 carbon. We have 1, 2, 3, 4, 5, 6. We have 6 hydrogen, and then we have 1 oxygen. This happens to be an ether, and we call it methoxymethane because we are having a met group here. We also have a methyl group here, methyl. So this is methoxymethane. The old name for this happens to be dimethyl ether, so showing the functional group which it belongs to. So we're going to be progressing to the main deal of the day, which happens to be stereoisomers. So stereoisomers, what are stereoisomers? Stereoisomers refers to isomers that have the same molecular formula, have the same structural arrangements, but they have different configurations in space. They have the same molecular formula, same structures, but then they have different configurations or different arrangements in space. That's spatial arrangement or spatial configuration. And for stereoisomers, we happen to have 2 types of stereoisomers. Now, stereoisomers happen to be divided into 2. We have 2 types of stereoisomers. So we have the configurational stereoisomers, and then we have the conformational stereoisomers. So but the configurational isomers happen to also be divided into 2 categories, and the configurational isomers, we have the geometric isomers, and then we have the optical isomers. All of these things you are going to be understanding them as the lecture progresses because they are quite deep. So you're going to be understanding it as the lecture progresses. So the optical isomers happen to also be divided into 2. So the optical isomers, we have diastereomers. Okay, I think I made a mistake. This is diastereomers, and then we have enantiomers. So this is like the category of isomers that we have. So under stereoisomers, we have configurational, we have conformational, we have geometric, we have optical, and under optical, we have diastereomers and enantiomers. So as we make progress in this particular lecture, you are going to be understanding these different isomers that are under stereoisomers, which is the basis on which you are studying stereochemistry and optical activity with regards to drug molecules. So the next focus we are going to be focusing on happens to be with regards to polarized light. Now, it is very, very important for us to study polarized light because polarized light is actually what we're going to use to understand optical activity. So, what do we mean by polarized light? Polarized light happens to be a light that vibrates in only one plane. A light that vibrates in only one plane. Now, if you look at sunlight or the light that comes from your electric bulb, you will realize that the light vibrates in different planes that are perpendicular to the direction of propagation. So, for example, let me just draw something very clearly that is going to help you understand it. So, let me assume that this is a bulb. Let me assume that this is a bulb. Now you realize that light that travel through this bulb travel on different planes. The light travels in different planes. So this is what we're having here. So the light is traveling in different planes. This is typical of your bulb light, your sunlight, and all of that. So, but when we're working with optical active materials, we have to provide lights that travel in one plane. And one way to do that is by using a device referred to as polarizer. So I'm going to be drawing a sketch picture or something that is going to represent our polarizer here. So this is like our polarizer in this place. What is the polarizer going to do? The polarizer will make only one vibration. That's a light that is vibrating in only one plane to get across to it. So with this polarizer, instead of having these multiple directions of vibrations crossing this particular part, we'll have just a single vibration on one plane crossing through. So that's what we refer to as this is what we refer to as polarized light. So this is the light source, this is the light source, and this is our polarizer, and then this is our polarized light. And it's very important, I have to let you know that the light we're talking about here is the linearly polarized light. Now, why do I have to highlight linearly polarized light? Is because lights can be polarized circularly and lights can also be polarized elliptically. So, but for the purpose of this particular tutorial, our focus is on linearly polarized light. Let me talk a little bit about polarizers before making progress. Now, polarizers happens to be equipments that or substances that you use to make light travel or vibrate in one plane. That is what we refer to as polarizers. And for polarizers, we have different kind of polarizers, and we have two basic types of polarizers. We have two basic types of polarizers. We have the absorptive polarizers, and we have the beam splitting polarizers. Now, these absorptive polarizers we're talking about, these ones are responsible. The way they operate, how they operate is that every other light that is vibrating in other plane is absorbed by the material, while the light that they want to cross through on one plane is the one that goes past the polarizer. So it works by absorbing unwanted signals of vibrating lights, and then the one that is necessary is what passes through it. But the beam splitting polarizer actually operates by splitting the light rays and making sure that the kind of light or the vibration of the light that you need to pass across is what passes across the particular material. And for knowledge purpose, it will interest you to know that we have an example of absorptive polarizer happens to be the Polaroid. Now, the Polaroid is made up of PVA. What is PVA? PVA is polyvinyl alcohol that has an iodine doping. So this is an example of an absorptive polarizer. While for the beam splitting polarizer, we have nickel. We have nickel prism. Now, nickel prism happens to be made of calcite, and calcite happens to be a type of calcium carbonate. Calcium carbonate, that is CaCO3. So its operation is by beam splitting. So outside these polarizers, we have polarizers that lead to circular polarization of light, and we have those that lead to elliptical polarization of light. So we have linearly polarized light, we have circularly polarized light, and we have elliptically polarized light. So when you want to work with circularly polarized light, you have to deal with the quarter wave plates. So, but like I mentioned in this particular lecture guide, our focus is on linearly polarized light, hence the focus on these types of polarizers. So let's make progress and begin to talk about optical activity. So I'm going to be talking about optical activity, which relates to molecules or compounds that are capable of rotating lights. So one of the instruments that is being used to study the rotation of lights by different compounds is polarimeter. Now the polarimeter, let me highlight the important parts of the polarimeter so you understand how it operates and how it relates to optical activity of molecules. Now we have the light source, we have the light source, they have the this now we refer to this as lenses. You can refer to them as lenses, but they are polarizers. So the first one serve as a polarizer, but then, like I said, these two, you can refer to them as two lenses. So, but then these are also polarizers. So, but the first one will serve as a polarizer. The one we are working with here, this one refers to as the sample tube. Now, the sample tube is where you put the sample that you want to understand the degree of rotation that is observed when polarized light passes through it. Then this second polarizer is referred to as analyzer. And then we have the human eye viewing it to check the angle or the degree of rotation. So now let's understand how this operates. Now this is a light source, and then it produces light that vibrates in different planes. So but when it passes through the first lens, which is a polarizer, and it can be called prism, or it can also be the other type of polarizer we talked about. So it now produces a plane polarized light, as you can see here. Now the sample that I want to analyze is already inside of this place, and usually measurement of optical activity is done on fluids, which fluids consist of liquids and gas, and it's usually with regards to aqueous solutions. So but there are some crystals that I can also study their optical activity, but mainly we study optical activities of fluids, which are liquids and gases. So but most of them are aqueous solutions. It's already dropped inside the sample tube. Now standard tube for polarimeter has a path length of 1 decimeter, and from normal mathematical relationship we know that 1 decimeter is equivalent or equal to 10 centimeters. So that's for standard polarimeter tube. So when it passes through the sample, if the sample is optically active, it will rotate the light. If the sample is optically active, it will rotate the light. So when it rotates the light, you can already see that the light is no longer the way it is now in a rotated format. You now use the next polarizer, which is now serving as an analyzer now, to be able to dictate the degree of the rotation, to look at the observed rotation of this particular light caused by the sample in the tube, and we refer to that as our alpha. And then with that, you can be able to analyze the different enantiomers of compounds and know the degree to which they rotate plane polarized light. So let's see how that can now apply in calculations, because basically compounds that exhibit this optical activity, they have mirror images that we refer to as enantiomers. Enantiomers, as we already saw, is a type of optical isomers, which is under configurational isomers, which is under stereoisomers, which is under the broad heading of isomers. So enantiomers refers to compounds that their mirror images are not superimposable. Their mirror images are not superimposable. For us to understand this very, very clearly, let me draw this structure and let us run with it. Now, this structure we have here happens to be a structure of propanoic acid. We have 3 carbons, and then we have a carboxylic acid group here. So this is propanoic acid. Now, if we run a mirror, on this, and then you get the mirror image of this, you're also going to be having a compound that goes this way. Now, this is the mirror image of propanoic acid. But then, So that you understand basically what we're having here, we have different kind of bonds that are captured in this place. We have the stick bond. These ones are plain. They are on this particular plane. And then we have the wedge bond, which is actually representing bonds that are coming out from this plane. And we have the hash bond, which represent bonds that are going away from this particular plane. So we're looking at this as a plane, and then we're using this now as the one to represent the bonds coming out, and this as to represent the bonds that are going backwards. What is the implication of this? It shows you that every of this molecule is not on the same plane. Every of these molecules are not on the same plane. We have those that are on this plane, which is represented by a stick bond. Then we have those that are going this way and the other going the other way, which are represented by the wedge bond and the hash bond. Now, the wedge bond happens to also be referred to as beta bond. Wedge bond also referred to as beta bond, while the hash bond also referred to as alpha bond. So it's very important to take note of those. Now, when we put a mirror here, you have a mirror image of the propanolic acid. You realize that what's changed? The only thing that changed is that the hydrogen that was at the front is now at the back, and the hydrogen that was at the back is now at the front. Now, you may look at this and be like, but these two hydrogens are still at the back. This is also this. Now, can we be able to redraw the structure so you understand clearly what has taken place at this particular point? So for us to look at this now, so it will appear the way this one appears, in this mirror image format, what we just simply need to do is to flip this thing by 180 degrees. So it will still remain on this plane, but then it's going to appear in this format. So let's flip it by 180 degrees. Now, the rule is, if you are flipping it by 180 degrees, the moment you flip it, you have to do one of two things. You either decide to change the substituents that are on the different bonds, or you change the bonds that are attached to the substituents. So let me draw this appropriately. So we are rotating it 180 degrees. So we're going to have this. We're going to have this. This is carbon, and then we're going to be having our hash bond, and we're going to be having our wedge bond. Like what did I say? I said that we're going to either decide to change the bonding attached to this, or change the substituents. Now, you can already see from propanolic acid that we have the same substituents. So whether you put hydrogen here and you put hydrogen here, or you decide to take this hydrogen and put it here, and take the other hydrogen and put it here, you still have the same compound. Now, let me ask you a question. This compound and this compound, are they not the same? They're exactly the same compound, and if you put this on this compound, it matches. That's what I refer to as superimposable. It is superimposable on its mirror image. But there are some compounds that are not superimposable. Those are the ones that have this optical activity. Now, for you to be able to understand that, let me draw the structure of lactic acid. So what we have here is still the structure of propanolic acid, but the moment you have a substituent of a hydroxy group here, OH, what you're having here is a lactic acid molecule, a lactic acid structure. Now, you're already seeing now that what we have here, we have H on this part and we have OH on this particular aspect. The moment you have the mirror image, you will have OH here. You have OH here. You can also write as HO because it's directly connected to the oxygen, which now links to the hydrogen. Now, how do we make this to look like this and such that it will still be representing a mirror image? Like I said before, first thing first, we flip by 180 degrees. The moment you flip by 180 degrees, the next thing you do is one of two things. It's either you put the substituents and change the bond, or you leave the bonds the way they are and change the substituents. Now, in this particular case, I'm going to change the substituents. I'm going to leave the bonds the way they are. So the HO, that's the hydroxy group, will now be on this particular bond because it was on wedge here. Now it is now on the hash or the dash bond, and then the hydrogen that was on the hash or dash bond is now present on the wedge bond. Now look at this very closely. This image is the mirror image of this, but cannot superimpose on this, because while hydrogen is going backwards and OH is coming out, in this particular mirror image, the OH is going backward and the hydrogen is coming out. So what we have here in lactic acid has optical activity. So we can say for sure now that lactic acid mirror images is not superimposable on itself. So the mirror image of lactic acid is not superimposable on the original molecule, and that is the basis for optical activity. So this kind of molecule will definitely lead to rotation of light, and then the degree to which it rotates light is a unique characteristic for each of those particular compounds. So we're going to be looking very quickly at some calculations that has to do with observed rotation, specific rotations, and how concentration of the molecule in the or the compound in the sample tube and the path length of the sample tube contributes to the degree to which rotation occurs in the polarimeter. So we're going to be looking at some calculations in optical activity to understand how to calculate for the observed rotations that you find after passing plane polarized light through a sample that is optically active. Now take note of this. We have what's called specific rotation. Now specific rotation is denoted by alpha in brackets, and then we have T over D, or we can also write it as alpha in brackets and then we just put D. Now let me explain what this refers to. Now alpha, this symbol represents specific rotation. Now specific rotation refers to the rotation that is specific for every molecule. Just like every compound has their melting point, has their refractive index, has their boiling point, and so on and so forth, specific rotation is a unique property of every particular chemical compound that expresses optical activity when you pass polarized light through it. So specific optical rotation is usually measured when you are using a sodium light. Now sodium lamp light has a wavelength of 589 nanometers. A wavelength of 589 nanometers. Now it is that wavelength that this sodium lamp that is represented by the D. The sodium lamp is represented by a D. Now the T happens to be the normal room temperature, used for such measurements, and usually what we have there is 20 degrees Celsius. That's what we have. So if you measure the specific rotation of a compound using sodium lamp and the temperature at 20 degrees, and another important thing again, with a standard polarimeter sample tube, like I told you, the polarimeter sample tube, the length of the tube is also referred to as path length. It's also referred to as path length, and the path length we are having here, we can denote it as L. And for a standard polarimeter tube, what we have is 1 decimeter. And then the concentration of the molecule, because the amount of the molecule is going to influence what you are having from this particular result. So when you have a concentration, now you can call it concentration or you can call it density. You can call it concentration or you can call it density. Now, when do you call it concentration? You call it concentration when it is a solution. When do you call it density? You call it density when it is a pure liquid. Take note of that. When it's a solution of like a solute and then a solvent, you work with concentration. But when it is a pure liquid and there's nothing dissolved in it, you work with density. When you have such of 1 gram per mil. So when you carry out the measurement for that compound with a sodium lamp of 589 nanometers and a temperature of about 20 degrees Celsius with a path length for the sample tube of 1 dm, and that's decimeter, and then a concentration or a density of 1 gram per mil, the degree of rotation you're going to have, or the angle of rotation you're going to have, is the specific optical rotation. So but then we are aware that different factors can lead to the different changes of the concentrations. So there's an equation that has been derived for it to relate observed rotation to specific rotation. So I'm going to be writing that equation out. So we have that our observed rotation is equal to specific rotation times path length times concentration. That is if it's an aqueous solution. Or we have observed optical rotation and then specific optical rotation times path length times D when it is a pure liquid. Solutions and then pure liquids. Solutions and then pure liquids. And then from this particular relationship, we can actually be able to calculate the specific rotation. So we have specific rotation, making it a subject of formula. Specific rotation is now equal to the observed rotation divided by the path length times either your concentration or your density. So that now makes us or gives us an idea of what the unit of specific rotation will be like. Now, this is measured in degrees. So we write degrees. That's the unit of specific rotation. That's what we're trying to talk about now. This is measured in degrees. So we write degrees. Now, this happens to be decimeter, dm. So we can write this as per dm, and then the concentration or the density is in gram per mil. So it's going to be mil minus 1, and then we have mil, and then we have gram minus 1, because the mil is already at minus 1, and then when you invert it, you just have your mil, and then you have per gram. You can also represent the unit as degree per dm per cm cube. Now, cm cube actually happens to be another unit for the mil. It's equivalent to mil. And then we have g minus 1. Now, if you convert your dm to cm, you can also have degree, you have cm minus 1, you can use your cm cube, or you can use your mil, and then gram minus 1. This is the one we usually find being used commonly, but any one of them can be used as a unit for specific rotation. So that is that about specific rotation. Now, one very important thing you have to take note of here is that when concentration is usually given, sometimes they give concentration in gram per 100 mil. They give concentration in gram per 100 mil. This refers to as percentage weight volume. And then when you have your concentration in gram per 100 mil, what do you do about your formula? Very simple. What you simply do is that you multiply the numerator using 100. So what we have is specific rotation is now equal to observed rotation times 100 over path length times concentration, and with that you have taken care of the concentration I was given in gram per mil. Now, it's also very important to take note of the fact that sometimes when you are giving concentration, you may not be giving any units for the concentration. According to scientists, what is being said is that when you find a concentration that doesn't have any units, you should assume that the concentration is in gram per 100 mil, and with that in mind, you can go to proceed with your calculations. Now, let me talk about the enantiomers. Now, seeing that each of these enantiomers can rotate light to different degrees, now one rotates it to the right, another one rotates to the left. Now, let me explain what names are usually given to such rotations. Alright, so we're going to be looking at the enantiomers, and then let me explain something very clearly. Now, when the substance rotates lights to the right, we refer to such enantiomer as dextrorotatory. And this dextrorotatory can be represented as D or by a plus sign. So you can use D and you can also use plus. And then when it rotates it to the left, this is for right, please. This is for right. Now, when it rotates it to the left, what we call that is levorotatory. So what we have is L, and you can also designate that as your negative. So that's what we used to refer to as optical activities of drug. So if you see something like this, lactic acid, it simply means that this enantiomer of lactic acid is responsible for the rotation of the polarized light to the left. While when you have the plus or D lactic acid, it means that the lactic acid we're talking about is the enantiomer that rotates lights, plain polarized lights, to the right. So it's very important you take note of that. Another thing you have to take note of is that this enantiomers rotate light to the same degrees, just that the difference is in their direction. So if lactic acid, for example, an assumption, rotates lights, for example, to, let's say, this one rotates to minus 23 degrees. The one that is dextrorotatory is going to rotate lights to plus 23 degrees. Do you understand that now? Now, on this particular basis, it simply means that if you have these two in a particular solution in equal concentration, as this one is rotating to minus 23, the other one is rotating to plus 23, and the implication is that you're going to have 23 plus 23 minus 23, and that's going to give us 0 degrees. So you're not going to have any rotation. So the implication is that you can have an optically active molecule in a solution, but it is not going to rotate plain polarized light because you have the two enantiomers at equal concentrations. Now, such type of mixture is referred to as racemic mixtures. Such type of mixtures are referred to as racemic mixtures. So what you're having here is not the property of the dextro rotatory, it's not the property of the level rotatory, it's a combination of the two properties. And racemic mixtures can go ahead and begin to exhibit different characteristics that are different from the level and also from the dextro. And in a polarimeter, they will not produce any form of optical rotation that can be observed, not because we don't have enantiomers there, but because we have enantiomers that are at equal concentration. Now, what do we mean by the term enantiometric SS? Now, enantiometric SS refers to a mixture that contains two of the enantiomers, but one of them is in SS. The implication is that that one decides the degree of the rotation that is going to be observed when it is placed in a polarimeter. So even if two of them are present, when you have one more in SS than the other, it is going to determine the observed rotation from the particular molecule. For example, let me assume that we have a racemic mixture that have an observed rotation of, let's say, plus 10 degrees. What it simply means is that you have both the dextro rotatory and the level rotatory in this particular racemic mixture, but because of the plus sign, it means that the dextro rotatory is more in concentration than the level rotatory. So enantiometric SS, like I already mentioned, is what's responsible for, like when you have one excess of one enantiomer responsible for the optical rotation. For example, let me assume that in a molecule you have the dextro aspect, you have it as 65% of the racemic of the mixture, and then for the negative, that's the level rotatory, you have it as 35% of the mixture. That makes up 100%. The implication is that what you're going to have it now for the percentage that is that is the enantiometric SS here is now going to be 65% minus 35%. Now, when you do that appropriately, it's going to be what? 30%. The implication is that the extra 30% of the dextro rotatory isomer, or dextro rotatory isomer that has the positive sign that's rotating to the right, is what's going to be responsible for the observed rotation of the mixture. So now let's look at some equations that are necessary for calculating the enantiometric SS before we proceed to some examples that will help us understand how to calculate specific rotation, observed rotation, and then the observed rotation for the mixture that we have here. So the specific rotation for the mixture of the two enantiomers is equal to the observed rotation divided by the path length times concentration. Now, if you want to calculate the percentage enantiometric SS, what you simply do is that the percentage enantiometric SS is equal to the percentage of the dextro isomer minus the percentage of the level isomer. So depending on which of them is SS, that's what's going to give you the percentage of enantiometric SS. Then another calculation again we can want to run here is how to now calculate for percentage enantiometric SS using these particular factors. So we have that the percentage enantiometric SS is now equal to the alpha specific mix of the mixture divided by the specific optical rotation of one of the enantiomers, one of the pure enantiomers, times 100. So the enantiometric essence for one of the pure enantiomers is the specific rotation we're having for it, the rotation of the mixture, and then the specific rotation for that particular isomer multiplied by 100 we get the enantiometric essence. All right, so we're looking at some questions today, and then we are going to be focusing on these two questions so I can get a basic grasp of how to use the formulas we have talked about earlier. And for the first question, it said a mixture with an enantiometric essence of 40% R has what composition of enantiomers? So I'm going to be dropping a formula that I've not dropped yet so you see how to solve this particular question. So when you're looking for the dextrorotatory isomer, you want to know the percentage present because it said what composition of enantiomers are present here. So the percentage present for the dextrorotatory isomer is equal to, in open brackets, 100 plus enantiometric SS divided by 2. 100 plus enantiometric SS divided by 2. Then when you are looking for the negative isomer, the amount of negative isomer, that's the level rotatory present, how you solve for that is 100 minus enantiometric SS divided by 2. So let us solve it now. So we already have 40% of R. So let us see, since R, we have 40% of R, it simply means that R is the one that is in SS. So for us to be able to know the amount of R present, we are going to solve now. So for the R, the percentage present for R will now be equal to 100 plus 40, because that's the enantiometric essence, 40%, divided by 2. 100 plus 40 is 140, divided by 2, that's going to give us 70. So it means that the amount of R we have here is 70% of R. Then what about if we have R already, what we'll now be looking for now is the amount of S present. You can decide that you want to do 100 minus 70 to get the amount of S present, or you could decide to use this formula. So 100 minus 70 will give us 30, but let's use this formula so you can see that the formula indeed is working. So the percentage present of X is equal to 100 minus 40 divided by 2. 100 minus 40 is going to give you 60, and 60 divided by 2 is going to give you 30%. So you can see that any which way you decide to go, you'll still get 70% of R and 30% of S. 70 minus 30 is going to give you back the enantiometric essence, which is 40% of R. So number one question, the composition is 70% of R and then 30% of S. So I'm going to progress to the second question. But the second question says morphine. Morphine has a specific rotation of minus 132 degrees. That means it is level rotatory, specific rotation. Now, if a student uses a sample that has a concentration of 0.0128 gram per mole and in a polarimeter of path length of 1 dm, that means it's a standard polarimeter, what would the student expect the observed rotation to be? So the thing we have to do quickly is for us to write down our formula. So the observed rotation we already know is equal to specific rotation times path length times concentration. So the specific rotation, according to our question, is minus 132 degrees Celsius. So that's minus 132 degrees, not Celsius, please. There's no Celsius, just the degrees. Celsius is for temperature. So minus 132 degrees. Then we are going to be multiplying by the path length. According to this, we have a path length of what? 1 decimeter. So our path length is 1. And then according to the question, we have a concentration of morphine of 0.0128 gram per mole. So what we have here is 0.0128 gram per mole. So minus 132, if you press your calculator, times 1 is going to give you minus 132. Then when you multiply by 0.0128, you're going to have minus 1.69 degrees. So the implication is that the observed rotation for morphine concentration of 0.0128 gram per mole in a polarimeter that is 1 dm even if morphine specific rotation is minus 132 degrees, it's actually minus 1.69 degrees. So that is the observed rotation. So we can now move on to talk more about chirality. Now, when we talk about a chiral substance or chiral object, I've talked about it before. We're talking about an object that has a mirror image that is non-superimposable. Non-superimposable. Now, every object has a mirror image, but the question is the mirror image superimposable on the object, or is it not superimposable? Now, most of the objects we know, for example, objects like football, for example, is always superimposable on this mirror image. But there are some objects like the human hand. Now, the human hand we have here, this is my right hand, this is my left hand. Now, this is like a mirror image of this, and it's like a mirror image of this. But look at this. It is not exactly the same. Where this one is not where this particular one is. Like the whole of my right hand, no matter how hard I try, can never be superimposed on this particular hand. So the implication is that what we have here are images, mirror images that are non-superimposable. So you call such objects chiral objects. So but the objects that have like that the mirror image can be superimposed on itself is referred to as a chiral object. So I'm going to be writing that down. So we have chiral. Chiral is when it is non-superimposable. Then achiral is when the image is superimposable. So when the image is superimposable, then we have an achiral object. So optical rotation only takes place in chiral object. Optical rotation does not occur in a chiral object. Another thing again you have to take note of is the fact that even if we have an object that has a mirror image that is not superimposable, if two of them are in same exact amount, we refer to such a mixture, I've said it before, as a racemic mixture. And a racemic mixture will not have any observed rotation. The reason is because while one rotated to a particular degree to the right, the other enantiomer is going to rotate it to the other degree to the left. And like another important information, like I mentioned before, is that the mirror image of one compound that is not superimposable on the other compound is referred to as enantiomer. It's referred to as enantiomer. You could also call it optical isomer. You could also call it optical isomer. So I'm going to be giving an example with lactic acid, and then I'll show you exactly what we're talking about. So let's draw the structure of lactic acid. So this is a carbon here, and then let's say we have a hydrogen here, and then we have an OH group here, and then we have a COOH group here, then we have H3C group here. Now this is the structure of a lactic acid. Now this acid, let's assume that what we have here is a mirror. Let's assume that what we have here is a mirror. So I want to draw the mirror image of this. So I'm going to have something like this. So this is going to be our H. Then we're going to have this our C. So we're going to be having OH here. Then we're going to be having COOH here. And then we're going to be having our CH3 here. So this is the mirror image of this. Now, just so that you're able to see what this looks like, if we're looking at it in this dimension, what you simply do is that you flip it 180 degrees. I've mentioned that before. Flip it 180 degrees and then change either the constituent of the hash and wedge bond, or you change the bond while leaving the constituents where they are. So what I simply mean is that when you move it 180 degrees, you're going to have the C this way, you're going to be having our COOH here, and we're going to be having our H3C here. But then We are going to be working with changing our bond instead of changing the constituents. We will learn about that as we make progress more better. I've highlighted it before and I'm going back to it again. So we are going to be changing the let's take the bond away. Let's just change the substituents. So the hash bond now, where we have hydrogen, we're not going to put OH, and then where we have OH initially, we're now going to be putting our hydrogen. So this image here is this particular image here. So the only thing is that I try to present it the way this other one is. Now you can see for yourself that initially this OH was at the front projecting outward while the H was projecting backward, but in the mirror image the OH is now projecting backward and the H is now projecting forward. So if you put this on this, they are not exactly the same, because while in this one OH is coming forward, in this one the OH is going backward, and same with hydrogen. So this is the mirror image of lactic acid, and because the two images are non-superimposable, you can simply say that lactic acid is chiral. You can simply say that lactic acid is chiral. Now let's talk about propanoic acid. Now propanoic acid, instead of having an OH here, you're going to have just hydrogen. So when you flip it, what you're also going to have here is hydrogen. And then when you flip it and then work on the bonds, what you are still going to be having here is going to be what? Hydrogen. So in this particular place, hydrogen is coming out, hydrogen is going out, hydrogen is coming out, hydrogen is going out. So these two images are superimposable. The implication is that they are chiral. The implication is that propanoic acid cannot be able to rotate plain polarized light, but from lactic acid can be able to do that, because we have enantiomers that are non-superimposable on each other. So we're going to be looking at the criterion for chirality. We just talked about chiral objects having non-superimposable image. Now, very importantly, what will make an object to be achiral is the presence of symmetry. The presence of symmetry will make an object to be achiral. Now, when we talk about symmetry, mathematically, it has its own definition. But for the purpose of this particular course, I'll just define symmetry as either a plane or a line or a point where there's corresponding similar shapes on both sides of that symmetry that we're talking about, or that reference point we're talking about. So when, for example, let's look at something like this. So let's assume that this is a square. Now you can say that there's a symmetry in this square because this side of this square is exactly the same as this particular side. You can say that there's a symmetry on this part because this side of this square is exactly the same with this other side. You can say that there's a symmetry on this part because this side of the square is exactly as the same other side. I'm just trying to explain to you what symmetry is all about. So presence of symmetry. Now there are three elements of symmetry. We have symmetry axis. Now symmetry axis can also be referred to as line of symmetry. Symmetry axis can also be referred to as line of symmetry. Then we have plane, or you can refer to it as mirror plane. So that's plane of symmetry. Then we can now talk about points, and we can refer to that as inversion. Now these three symmetry elements have their own role to play when it comes to definition of symmetry, and then these three symmetry elements now works with 5 symmetry operations that we're going to be looking at very, very shortly. So there are 5 symmetry operations that work with these 3 elements of symmetry, and I'm going to be starting with the first symmetry operation. What we have in the first symmetry operation is n-fold rotation. And is represented as Cn, where n is an integer. So this actually refers to a rotation of 360 degrees divided by n. N can be 2, n can be 3, n can be 4, n can be 5, and so on and so forth. Now when a compound has a particular number of rotation, for example C2 here, that is when n is 2, is going to be 360 divided by 2, that's going to give us 180 degrees. Now C3 here when n is equal to 3 is going to be 120 degrees. Now C4 here when n is equal to 4 is going to be 90 degrees, and so on and so forth. Now when a molecule actually has any form of rotation, n-fold rotation, such that when it rotates in any of these folds, it gives back the original rotation, it means that it has an axis of symmetry, or it has this symmetry operation, n-fold rotation. So let's use water as an example. So this is the structure of water. So we have oxygen connected to hydrogen, connected to hydrogen. So this is water. Now if you rotate water 180 degrees, if you rotate water 180 degrees, it means that first of all, this water is going to come out and then it's now going to go back. So this first coming out is 90 degrees and then going back is 180 degrees. You will now have this hydrogen will now be on this side, and then this hydrogen will now be on this side. You are still having the same molecule. So it means that water has a C2 n-fold rotation, because with 180 degrees you are getting exactly the same image. So it means that water is achiral because it has an axis of symmetry. So the element of symmetry being used here is axis of symmetry, also known as line, of symmetry. But then let's look at, if you turn water 90 degrees, that means what is like this, you turn it 90 degrees. This is what we're now going to have. Our water will now have okay, we now have a wedge bond hydrogen, because one hydrogen is now outside. Then you now have a hash bond hydrogen, but the other one is now at the back. Now this image and this image are not the same. The implication is that water does not have C4 rotation, because what we have here is a 90 degrees movement of water. So it means that water does not have C4 rotation, but water has C2 rotation to give it the exact same image. So that is that about n-fold rotation. Now the second symmetry element we're going to talk about is reflection, and reflection is represented as sigma. And then reflection actually works with the elements of symmetry referred to as plane of symmetry, and we also call that mirror plane. Now, plane of symmetry simply means when there's a plane on the compound that gives it a mirror image, like the two parts between that particular plane is going to give a mirror image that exactly the same. So for easier understanding, let's also use water and let's see what it's like. So this is water, O, and then we have H, Now, if you have a plane here, plane is different from line. This is line. But when we talk about plane is like a flat surface. So if you have a plane that is cutting through this place, okay, let me see if I can draw anything. So this is like a plane that is cutting through this place. So when you are talking about plane, you want to look at something, just any flat surface cutting through this. You find that this side of the molecule, that's the H here, is same thing as this side of the molecule. So since these two mirror images are the same, you can simply say that water has a plane of symmetry. Now, from what you are saying, you can already see that water has a vertical plane of symmetry. Usually, we can represent that as sigma V, a vertical plane of symmetry. Now, another plane of symmetry we can still see in this water is what we refer to as external plane of symmetry. Now, external plane of symmetry simply refers to the plane that occurs when the plane cuts through the molecule. For example, this is a flat drawing, and from what we are seeing already, we can see that this bond, stick bond, is representing this flat surface. Stick bond is representing this flat surface. I told you that the wedge bond means that it is coming out, and the hash bond means that it is going back. So these ones are on this particular surface. So if you have a plane that cuts through this particular surface, that's a plane that is like this, for example, just something that cuts. Let me draw it fully. But it's not cutting only the bond, it's also cutting through the elements. So something that cuts through this completely, something that cuts through this some completely, what you have at the front is going to be equivalent with what you have at the back, because there's no other molecule probably going outside or any molecule coming outside. Everything is on this surface, so you can cut right through it, and the front will also be reflecting the back. Now that kind of symmetry is referred to as external plane of symmetry. External plane of symmetry. So anytime you have a structure that just has only stick bond, usually you will find an external plane of symmetry. The implication is that it can never be carried out because a plane of symmetry is present. Let's look at another compound, so I'll come to understand another important part of this. Let's look at xenon tetrafluoride. Now xenon tetrafluoride is XaF4. So this is xenon, and then we have fluorine atom, we have fluorine atom, we have fluorine atom, and we have fluorine atom. So this is xenon tetrachloride. Now if we use a plane on this place, this side is a mirror image of this side. So we have one vertical plane of symmetry. If we use a plane that goes this way, we have two F's here and we have two F's here. This is a mirror image of this particular one. So it means that there's a diagonal plane of symmetry. If we decide to go this way, we'll have fluorine here and we have fluorine here. These two sides are mirror images of this each other. So we can also refer to this as horizontal plane of symmetry. And like I already told you, the moment you have stick bonds all through, it means to also have an external plane of symmetry. So let's count how many planes of symmetry does xenon tetrafluoride has. It has 1, 2, 3, and 4. So we have vertical, diagonal, horizontal, and then the external plane of symmetry is also a vertical plane of symmetry. Now, these ones that are inside are referred to as internal plane of symmetry, while the one that is external is referred to as external plane of symmetry. So both the external and this vertical are both vertical, while this is diagonal and this is horizontal. So those are the two symmetry operations that have been taught about so far. So let's go ahead and talk about the remaining three, and then we'll make progress on this particular lecture. Number 3 is going to be inversion. Now an inversion is represented as I. Now the symmetry element that works with inversion is the inversion point or point of inversion or center of inversion or inversion center. So that is the symmetry element that works with this particular symmetry operation. Now what do we mean by inversion or points of inversion or inversion center? What we're talking about is that in that particular molecule, if you take every atom to the opposite side, let that atom relate or superimpose on another atom that is exactly like it. The moment you have a particular center where movements of atoms directly opposite themselves superimpose on an atom that is similar to it, the implication is that that element or that compound has an inversion point or has an inversion center. So for clearer understanding, because I understand that practical based things or examples will help you to understand the concept of these things much more effectively, we are going to be working with 1,2 dichloroethane, and then we're going to be working with the trans version of it. So let me draw dichloroethane for you to understand that better. So this is carbon. Since it's ethane, we have 2 double bond. Then since it is a cis, you have chlorine, you have hydrogen, you have hydrogen. Now let's move. Obviously from this point, the center we have here is at the center. So let's move each atom and see if it's going to have the same image on each side. If you move chlorine directly opposite itself, it will be on hydrogen. Hydrogen is not something as chlorine. So the implication is that here it cannot be referred to as an inversion point or a center of inversion in an inversion center. Now, if you move hydrogen from this point to this side, hydrogen is not chlorine and chlorine is not hydrogen. So the implication is that here cannot be referred to as an inversion center for cis 1,2-dichloroethane. How about if I'm not working with trans 1,2-dichloroethane? In trans, what we're going to be having now is that instead of our chlorine to be up, we're going to be having our chlorine down here, and we're going to be having our hydrogen down here. Now, if you move your hydrogen to this particular point and you're moving this one here, they are replacing each other, they are same atom. If you move your chlorine here and you move this one another one here, they are replacing each other, they are same atom. So the implication is that this place is going to be a center of inversion for trans 1,2-dichloroethane. Another very good example of this is our benzene ring. So let's look at our benzene ring. So this is our benzene ring, and we have yeah, we have hydrogen, and then we have hydrogen. Now this is our inversion point. Why is it an inversion point? Because if you move this hydrogen to this point and you move this one here, move this to this point, move this one here, move this to this point, move this to this point, you will still have the same benzene ring. So nothing changed. So the implication is that there's an inversion center here. So any compound that has inversion center or inversion point automatically will be a chiral. Simple tip. You will already see for yourself that benzene is a chiral. One of the reasons is because it has a center of inversion altogether. So the other two symmetry operations, the other one we have improper rotational axis of symmetry, or you can also call it rotation reflection axis of symmetry. Now this is represented by a symbol XN. For the purpose of this particular tutorial, we're not going to be going deep into this because it's going to be quite complex and will not really serve the purpose for which we are doing this tutorial. So you could always request if you need more explanation on this. Now the fifth one, which is very simple, is the identity operation. Now the identity operation is represented as E, and what it simply means is that you are rotating the image by 360 degrees. If you rotate something by 360 degrees, automatically it will get back to where it started from. So identity operation will definitely give you the same image of that particular object, and it's as good as multiplying the object by 1. So what you are having in identity operation, every molecule, every compound has the identity operation. So with this in place, we have been able to look at all of the symmetry operations we have in this particular tutorial. So what we're going to be looking at now is how to identify plane of symmetry. I've already told you before that plane of symmetry simply means, like, plane simply refers to like a flat surface. Plane simply refers to like a flat surface. So we're going to be looking at how to identify planes of symmetry quickly with several examples so that you can grasp how to identify these things and know when an object is chiral and when the object is achiral. So we're going to be looking at the planes of symmetries in these different compounds that were drawn on the board. So we're going to be starting with the first compound. Remember, any compound that has symmetry automatically will be a chiral. But when it lacks symmetry and it's in order, then that compound becomes chiral. The implication is that it can be able to rotate plane polarized light. So let's look at this first compound. This is methane. Methane is 1 carbon and then 4 hydrogen. So let us see the planes of symmetries that are present in this compound. Remember, wedge bond means it's coming out from the plane, the hash bond means it's going away from the plane, and then the stick bond means that it is right on the plane. So this particular compound has 6 planes of symmetry. It has 6 planes of symmetry. Now, what do I mean by that? For example, if you have a plane that is running through your H1, through the C, and then through the H2. What I mean by that is that you're having a plane that is cutting across H1, C, and H2. What you're going to be having on the remaining both sides is H4 and H3. Are you getting the point now? So what you're going to be having on both sides is H4 and H3, and 2 of them are same hydrogen. The implication is that you have a mirror, so that is a plane. Another plane you can have is that you can say, okay, let's have a plane that cuts through H1, C, and H3. The moment you have that plane, a plane that runs through H1, C, and H3, 3. The moment you have that plane, what you're going to be having reflecting on both sides is H2 and H4, and two of them are HH. The implication is that there's a plane of symmetry on that. Another plane of symmetry we want to run is, okay, let us cut through this. So remember, you're having this coming forward, this one going backward. You're cutting through this particular plane. So you're going to be cutting through H1, C, and then H4. So you're going to be having a reflection of H3 and H2. Are you getting what I'm saying? Now, you're going to be having a reflection of H3 and H2, and since both of them are hydrogen, the implication is that that's a mirror plane. Another thing again you can decide to do is that you can decide I want to cut through H2, C, and H3. Now, since, for example, now look at this. So since our H2 is at this back, our H3 is at the front, and then our carbon is this way. So you can cut through it. The moment you are cutting through it, you're going to be having this H1 at the top, you're going to be having H4 at the bottom. So by implication, these two are going to be mirror images, and you're going to be having H2, a plane of symmetry running through H2, C, and then H3. So these two will be mirror images, and that's going to give you a plane of symmetry. You could also decide that you want to do H2, carbon, and then H4. So you're going to be having H2, carbon, and H4. You're going to be having hydrogen 1 and hydrogen 3, and H1 and H3 being mirror images of each other. The implication is that you're going to be having a mirror plane of H2 through carbon and through H4. So the mirror is what? H1 and H3, and since both of them are hydrogen, it means that this is a confirmed plane of symmetry. Now you could also decide you want to do your plane of symmetry between H3, carbon, and H4. So the mirror image now be between H1 and H2. That mirror image is already make this one like its own plane of symmetry. So this is H3 to carbon to H4. So how many planes of symmetry have we counted already? We have 1, 2, 3, 4, 5, 6. So what we have here is 6 planes of symmetry. So let's go to the next one now. This carbon has bromine, chlorine, and hydrogen. And the question you ask yourself is, does it have a plane of symmetry? Now let us see that. If you cut through hydrogen, carbon, and bromine, you have bromine and chlorine left. These two are not mirror images, so this is not a plane of symmetry. If you go through hydrogen, carbon, and bromine and chlorine are not same thing, so this is not a plane of symmetry. But if you go through hydrogen, carbon, and chlorine, that's you are cutting through this way. So what we have is hydrogen, carbon, and chlorine are cutting through this way. You're going to be having bromine at the front, and you're going to be having bromine at the back, as you can already see on this bond, and two of them are same. So the implication is that you're having a mirror image of bromine. So we have a plane of symmetry that cuts across hydrogen, carbon, and chloride to give a mirror image of bromine and bromine. So the implication is that this particular compound is also alkyl. So let's just put that here. This is alkyl, and this one we said it has 6 planes of symmetry, and this one has 1 plane of symmetry. Now we can't have an external plane of symmetry here, because when you have an external plane of symmetry, the only thing that we cut is H, carbon, and Cl. It's not going to cut through bromine, it's not going to cut through this bromine, because these two are not on the plane of the paper. While one is going backward, the other one is coming forward. Are we making sense now? So let us look at this second compound, so you understand the third compound, so you understand what we're talking about very appropriately. Now this is carbon attached to hydrogen, fluorine, bromine, and chlorine. So let us see if we are going to find any plane of symmetry. Now if you have a bond that is a plane that is cutting between hydrogen, carbon, and fluorine, you have chloride and bromide, chlorine and bromine, that's not same image. So the implication is that that's not a plane of symmetry. Hydrogen, chlorine, carbon, and bromine, we are going to have chlorine and fluorine. These two are not same elements, so the implication is that that's not a mirror image and it doesn't have a plane of symmetry on that regard. Hydrogen, carbon, and chlorine, we are going to have bromine and fluorine, so there's no mirror image. The implication is that this compound has no plane of symmetry, and when it doesn't have a plane of symmetry, we simply say that this compound is chiral, so it has 0 plane of symmetry. Now for you to just take note, whenever you have a carbon that has 4 different substituents attached to it, that carbon or that compound is usually a chiral compound. So it's very important you take note of that. Now let us go to this particular compound. Here we have carbon double bonded to each other, and then we have hydrogen. This is an 18 molecule. Now let us see the number of planes of symmetry we have there. First of all, we have a vertical plane of symmetry. Now we have hydrogen, carbon, carbon, hydrogen. So these two places are mirror images of each other. So we have 1 vertical plane of symmetry. How about through this place. So I have a horizontal plane of symmetry because hydrogen is mirror image of hydrogen. Hydrogen is mirror image of hydrogen. So this is also going to have a horizontal plane of symmetry. Another plane of symmetry that is very important, like I mentioned, since all of them are on this particular plane, we can slice through it. We can slice through it. So at the front side will be reflection of the back side. So the implication is that this will also have an external plane of symmetry. So the implication is that here we have three planes of symmetry, one vertical, one horizontal, and one an external plane of symmetry. And by implication, this molecule is a chiral. So let's look at this particular molecule also. So this is carbon, carbon, bromine, bromine, hydrogen, hydrogen. Now, what planes of symmetry do we have here? This is not a plane of symmetry. The implication is because bromine is not same as hydrogen, and hydrogen is not same as bromine. So here cannot be a plane of symmetry. Same way, here cannot be a plane of symmetry because bromine is not same as hydrogen, and hydrogen is not same as bromine. But we have one plane of symmetry that is here. Because all of these bonds are on a flat surface, the implication is that we must have an external plane of symmetry that is slicing through it. So at the front, we'll be reflecting the back. So by implication, we have one external plane of symmetry, and this is going to be a chiral. Now let's look at this particular one also. We don't have a plane of symmetry here because bromine is not hydroxyl group and hydrogen is not chlorine. We don't have a plane of symmetry here because bromine is not hydrogen and hydroxyl group is not chlorine. But we have one plane of symmetry because this is on a flat surface, and that plane of symmetry is external plane of symmetry that's going to slide through it. So it has one external plane of symmetry. By implication, this molecule is a chiral. So let's look at this particular molecule also. What planes of symmetry do we have here? First of all, we have a horizontal plane of symmetry. The implication is because we have a methyl group here that's also reflecting another methyl group here. So this is a horizontal plane of symmetry. We cannot have anyone here because we don't have any mirror image of this on this particular side. But then, because all of the bonds are on the flat surface, there's one plane of symmetry we have there. You're already guessing it, right? An external plane of symmetry. So the implication is that we have two planes of symmetry here. One is horizontal, and we have the other one as the external plane of symmetry. So the implication is that this molecule is going to be a chiral. So let's look at the last one. This particular one, before we go to further examples and begin to look at ring structures. Now, this particular compound happens to have C double bonded to C double bonded to C. Now I'm going to tell you the name of this kind of compounds as we progress in this particular lecture. You will realize that we have methyl group on the stick bonds, and then we are having on this particular side we have dash bond and wedge bond. The implication is that all of the bonds are not on the same plane because we have the one that is coming forward and we have the one that is going backward. So the implication is that first of all, we are not going to have an external plane of symmetry because once you are cutting it this way, it will not cut through this hydrogen, it will not cut this hydrogen because these ones are coming out, the other one is going backwards. So what we're going to be having here is that first of all, we will have we have a plane of symmetry that is vertical. Now let me explain the vertical I'm talking about. When you cut through this, it is going to cut through this bond, this, leaving behind only the hydrogen and this hydrogen. Now these two are mirror images, so the implication is that we have one mirror plane that is what? Vertical. Now another way again we can go to work on it is that we can work on horizontal plane. Now if you cut this horizontally, remember that what we have here is hydrogen, and then you are cutting it horizontally. So you're going to be cutting through both the hydrogen at the front and the hydrogen at the back, and then you're going to be cutting through this carbon, and carbon. So what you'll be left with is methyl group and methyl group, and since two of them are mirror images of each other, it means that you have another plane of symmetry here. So we have a plane of symmetry on this basis, and we have a plane of symmetry that is vertical, so horizontal and vertical. So we have two planes of symmetry, but none of them is external. The reason is because these two are not on the same plane such that it will be able to cut through all of them. So we have two planes of symmetry, horizontal and vertical, and it's going to make this molecule to be a chiral. So let's look at more examples. So we have some cycloalkanes we can use to understand identify planes of symmetry. So let's look at this very one here. So this cycloalkane we have here, we have a wedge bond that connects a methyl group and a stick bond, a hash bond that connects a methyl group. Now, can we call this a plane of symmetry? We cannot call this a plane of symmetry. The reason is because why this one is going forward outside. This one is going backwards, so they are not mirror images of each other. What you're having here and what you're having here are not mirror images of each other because of the distinctiveness in the bond. Assuming this bond here happens to be a wedge bond, it means that you can have them as what? Mirror images. So this does not have a plane of symmetry, and by implication, it is a chiral compound. It is a chiral compound. So let's look at the second one. Now, does it have a plane of symmetry? Yes, it does have a plane of symmetry, and the plane of symmetry we have here is this plane of symmetry because this side is mirror image of this particular side. So this is a plane of symmetry, and by implication, this compound is a chiral. This compound is a chiral. What about this particular compound? How many planes of symmetries do we have? Now, this is a plane of symmetry. So this side is same as this side, so it's a plane of symmetry. We also have a second plane of symmetry because this side is a mirror image of the other side. So the implication is that this is an achiral compound. How about this particular compound? This is methyl group here and this is ethyl group here, but here is a plane of symmetry such that here is equal to this, but we don't have a plane of symmetry this way because while we are having a methyl group here, this is an ethyl group. So the implication is that this one has only one plane of symmetry while this has two planes of symmetry. So how about this one? We have a plane of symmetry here. We have a plane of symmetry here because this is going backwards and these two are coming forward, so they are mirror images of each other. Now you cannot have a plane of symmetry this way. The implication is because this is a wedge bond coming forward and this is a hash bond going backwards, so they are not mirror images of each other. And if you go this way, these two are not mirror images of each other, but these two that are coming forward are mirror images of each other. So the implication is that you have just one plane or symmetry on this particular compound. How about this compound? All of them are coming forward, so you have a plane of symmetry that divides it into these two, you have a plane of symmetry that divides it into these two, and then you have a plane of symmetry that divides it into these two. So the implication is that we have three planes of symmetry, and all of these compounds that have planes of symmetry are achiral compounds. So I think with this very clearly explained examples, you should be able to identify planes of symmetries in any particular compound you encounter. So we're going to be working on molecular geometry and then we'll make progress. So let's look at some molecular geometry shapes and then see some very important definitions that can help you understand a few things. So we have different shapes or geometry of shapes. We have linear, we have trigonal planar, we have bend shape, also known as V-shaped, and you can also refer to it as angular, and then we have the tetrahedral shape, we have the octahedral shape, we have the square planar, and we have the trigonal pyramidal. So let's start with the linear shape. Now, linear shape is when you have, let's say, a bond that is connected on a straight line. So an example is carbon 4, like this is carbon, double bonded to oxygen, double bonded to hydrogen, and it's on a straight line. So we refer to that as linear shape. Another example can be nitrogen 4 oxide, that's NO2. So it has an angle of 180 degrees, an angle of 180 degrees because on a straight line. So the next one we're talking about is trigonal planar, where we have a molecule bonded together in such a way that it forms a triangle, but then the bonds are on a plane. So that's why we refer to it as trigonal planar. It's different from trigonal pyramidal. When we get there, you understand better. So this is on a plane, and the bond angle between any of the two, any of the bonds is 120 degrees. Then we have the angular shape, which is also referred to as bend shape, or also referred to it as V shape. And the angle of between the two bonds is 105 degrees Celsius. An example is water, that is H2O. So that's what we have there in that particular structure. Another shape we have is tetrahedral. In tetrahedral, we have a carbon that is or an atom that is bonded to 4 different atoms. So here we have methane, where that's CH4, where we have a carbon that is bonded to 4 different hydrogens. So the bond angle between any of the bonds is 109.45 degrees. So this is a tetrahedral shape having 4 sides. Then the next one we have is octahedral shapes. Now in octahedral, we have 8 bonds. Let me see if I can be able to sketch the structure of a tetrahedron so that you can understand basically what we have here. So let's see if that is obtainable. Yeah. Let's see if I can be able to sketch the structure of an octahedron. Okay, yeah. So we can have something that is coming. Sorry, can have something that's coming this way, and then that way and that way. Okay, I'm just trying very hard to be able to sketch something like a tetrahedron, but if we want to look up that image probably online. Now, in this particular tetrahedron, we have eight different sides: one, two, three, four outside, and then at the back we have one, two, three, four. I don't know if you get what I'm saying. So this what we're having here is just like the front part of it. I was trying to sketch the back using these dotted lines. So at the back also, when we have one, two, three, four at the front, at the back also we also have one, two, three, four behind it. So those are eight sides, and then working with the eight bonds. So that's what the kind of structure you can have from something like sulfur hexafluoride. Sulfur hexafluoride. So you have six atoms of sulfur, but then you're having like eight sides. So that's exactly why we're referring to it as octahedral. So it has eight bonds that are working together, and the bond angle is 90 degrees. So another one again we have is trigonal pyramid. In trigonal pyramid, we have a shape that has something like a triangular base, like a triangular base. But like I told you, this one is on a plane, this one is not on a plane, because we are having a wedge bond and also a corresponding hash bond. So this is trigonal pyramidal, and the angle between the two bonds is either between greater than 90 degrees but less than 109.5 degrees. So the last one we're going to be talking about is the square planar. Square planar simply means you have four different bonds in a square shape or in a square arrangement in such a way that the angle between all of them is 90 degrees. An example of square planar bond, where you find square planar bond is xenon tetrafluoride. Now, one very important thing you have to notice is that any of these shapes or any of these geometrical shapes or arrangements that is planar, we usually have what we have already explained, which is the external plane of symmetry, because you can cut through it. For example, this carbon that is linear, you can cut through it. It means it has an external plane of symmetry. This particular one, you can cut through it. It means it has an external plane of symmetry. So that's NH3. So this particular one, it has an external plane of symmetry. You can cut through it. So this square planar, you can cut through it. So the implication is that any structure that is planar will always have an external plane of symmetry, and the implication is that planar structures can never be chiral, because the plane of symmetry automatically has already cancelled out the criterion for planarity. But then when we have shapes that are tetrahedral, we have shapes that are octahedral, or we have shapes that are trigonal pyramidal, with appropriate substitution and arrangement, it is most likely you can avoid having any form of plane or symmetry. The implication is that for compounds that are either tetrahedral, octahedral, trigonal, pyramidal, that doesn't have flat or planar structures, that is where you can go to find chiral compounds, and then that is if they are properly substituted and if they are properly arranged in the particular structure. But any structure that is planar, that does not have any wedge bond or hash bond, that structure will never be chiral, because there will always be an external plane of symmetry. So let's look at the meaning of disymmetric and asymmetric as we make progress in this particular lecture. We're going to talk about disymmetric compounds and then asymmetric compounds. Now, when we talk about disymmetric simply means that the compounds are lacking in two elements of symmetry. Okay, let me write that down here. So for disymmetric, we are having an element or a compound, sorry, that lacks two elements of symmetry. That is the plane of symmetry, and then we have the points of inversion or the inversion center or the inversion point. Now, a compound that is disymmetric has the capacity of being chiral. A compound that is disymmetric has the capacity of being chiral. So the moment you lack plane symmetry and you lack points of inversion, automatically you become a chiral compound. But then when we talk about asymmetric simply means that the compound lacks three elements of symmetry. We have the plane, as we have here, we have the points, and then we have the axis of symmetry. So this one lacks three and this one lacks two. Now, once you've already lacked two, or any compound already lacks plane of symmetry and points of inversion, it must be chiral. But then it does not necessarily need to lack the three of them for it to be chiral. Now, this is what it implies. It implies that asymmetric compounds are always chiral, but chiral compounds are not always asymmetric. So why exactly do we have that? Asymmetric compounds are already lacking the three elements of symmetry, so they are always chiral. But chiral compounds are not always asymmetric. The reason is because chiral compounds could also be disymmetric. And like I mentioned, the moment you lack plane of symmetry and point of inversion center, you automatically become chiral. So asymmetric compounds will always be chiral, but chiral compounds will not always be asymmetric because some chiral compounds can be disymmetric. So carbon, asymmetric carbon, like when we have a carbon having four different substituents, can also exhibit chirality. And apart from compounds that has carbon, compounds that has things like sulfur, compounds that have phosphorus, compound that has nitrogen can also show some level of chirality if the substituents and other things are put in order.